So this is the first lot of calculations. Question 3 was about empirical formulae, and actually some people don't cover this at GCSE, and therefore I'm going to go through it nice and slowly so that you understand, because it's actually quite an easy calculation and you will definitely have to do it at A level. Okay, so finding an empirical formula, we've got potassium, nitrogen and oxygen. So the first thing I do is lay it out with my 3 elements with their symbols. And basically this is just a mole calculation. So if I want to know the formula of something, and actually for ionic compounds, which this would be because it contains potassium, the empirical formula is just a formula. It's just what the formula would be. We'll talk about why that is when we look at bonding. But if I want to know the formula tells me how many moles of each type of atom, or how many individual atoms there are. Atoms is proportional to moles. So actually all I need to do is find the number of moles of each atom that's present, and then I can get it down to a ratio, a whole number ratio. So the thing at the moment is what I've got given in the question is I've been given mass. So to get moles from mass, I just need to do mass divided by, in this case, the atomic mass, because these are single atoms rather than formulae. So I'll go on the periodic table, I'm going to find relative atomic mass, you might call it RAM, and I'm going to find out that potassium is 39, nitrogen is 14, oxygen is 16, and then I'm going to divide those masses in grams by those relative atomic masses, and I'm going to get my moles out of that. So I get 0.15 moles of potassium, 0.15 moles of nitrogen, and 0.3 of oxygen, and quite easily I can see that my ratio is 1 to 1 to 2. And what I mustn't do is forget to actually write the formula. Don't just leave it there and go, I found my numbers. So this empirical formula technically isn't too different from the last one, but it looks a lot different for some reasons. So one thing is you've not been told, doesn't look like you've been told the elements, but you have, because you've been told it's a hydrocarbon. So what I know from that is that it only contains carbon and hydrogen. Then we've been given percentages. So previously we had actual masses, and it was easy to see that if you have the mass of an atom or an element, you can work out the moles. You can do the exact same thing with percentages, and the reason you can do that is because, remember, we're only trying to find the relative ratios. The exact amounts aren't important. So what I'm going to assume is my whole sample of hydrocarbon weighs 100 grams, and if it does, then my mass of carbon in that sample is 83.7 grams. And if my whole sample weighs 100, then the mass of my hydrogen is 16.3 grams. From then on, I'm going to follow so far the same method. Find the atomic masses on the periodic table, divide the mass in grams by atomic mass to get mole, and I get 6.975 moles of carbon for every 16.3 moles of hydrogen. Now, if you've done empirical formula before, the next thing you'll be told to do is divide by the smallest number, and a lot of people just learn that. And the reason we're doing that is just because we're trying to get a simple ratio. So usually, like in the previous question, if we divided everything by the smallest number, then some of our numbers became 1. For example, if I obviously divide 6.975 by itself, I'll get 1. And usually what happens is you then get the rest of them being very close to whole numbers. Now if I divide 16.3 by 6.975, so I'm just trying to whittle down this ratio, I actually get an answer of 2.33. So that's like my ratio, but that's not a whole number ratio. So when this happens, the numbers should be really close to whole numbers, and if they're not, you need to do something to them to make them whole numbers. So in this case, obviously one of them is 1, and that is a whole number. Other examples you might get would be, for example, 6.975. I could confidently round that to 7. If I had 1.98, I would confidently round that to 2. If I had 1.5, I would not round that to 2. I would see that that is exactly halfway, and I would times it by 2 to get 3, and I would times everything by 2. In this case, you can see that I've basically got 2 1/3 as my answer. So I don't want to round that down. I want to times everything by 3, and that is just to get a whole number. And if I do that, I will get 3 to 7. So my empirical formula, the simplest ratio of atoms, is C3H7. Now that isn't a real molecule, and that's why the question has given me the relative formula mass of the compound, which is 86. So what I'm going to do is I'm going to find out the mass of C3H7, because I know that that's the simplest ratio of elements. So my empirical formula has got to fit in somehow into the formula of the whole compound. So if you're struggling with this, an example, if you think about alkenes all have the formula CnH2n. So there's ethene, and there's propene C3H6, and there's butene C3H8. Can you see that they would all have the simplest whole number ratio, because they all have the same relationship between carbon and hydrogen? Hydrogen is always double. So they all have an empirical formula of CH2, but they all have different molecular masses because they have different actual molecular formulae. So I would have to know the mass of those in order to work out, or the relative formula mass, to work out which one it was. So in this case, I've got C3H7. I'm going to work that out. The MR of C3H7, which is not a real molecule. If you try and draw that with displayed formula, it doesn't work. So I've got 3 times 12 plus 7, and that gives me 43. And hopefully we can see straight away that 43 goes twice into 86. So I need to times that formula by 2, and the whole formula, the molecular formula, is therefore going to be C6H14. That's good because that fits the general formula of an alkane, so that's a sensible answer. You will get some that you haven't seen before with slightly less hydrogen, but generally it should be something that you're familiar with. Okay, hydrated salts is again something that you might not have covered at GCSE, but it is a mass mole calculation. So I've got some information about sodium sulfate, and I know that there is some water. So the way that I'm doing this is similar to with elements, but I'm writing the formula of the whole compound, but I'm still going to put in the mass of each one. So I definitely know I've got 7.05 grams of water. I've not got 15 grams of Na2SO4. So this hydrated salt, is a compound that contains ionically bonded sodium sulfate. Water is obviously covalently bonded, and then these waters of crystallization stick to the sodium sulfate. You've seen this with copper sulfate. Copper sulfate, hydrated copper sulfate, is blue, and then it turns white when you heat it, and that's anhydrous copper sulfate. So how many grams of Na2SO4 have I got? Well, I just need to take away the 7.05 from the 15, because there's only Na2SO4 and H2O in my solid. So 1 mark would be for working out, I do this every time, 7.95 grams of sodium sulfate. From there, instead of doing atomic masses, I'm going to do relative formula masses. So MR, if I work out sodium sulfate, it has an MR of 142. In the answers it might say 142.1, and that's because it was taken from an A-level periodic table. Don't worry about it. Water is 18. So then we just do our mass moles calculation. So even though we're a little bit stuck because we've not seen this sort of thing before, we can just do it using the idea that if I've given the mass in grams of a substance and its formula, I can work out how many moles there are. So I've got these two numbers, moles, they're not whole numbers. I want them whole numbers, so that's when I divide by the smallest number, and I should always be doing this for waters of crystallisation. If we have a look at that formula at the top, there should be 1 mole of the salt, Na2SO4, and X moles of water. So how your calculation should be working is that the salt should always be the smallest number, because there's always more moles of water than there are of the salt. So if that's not the case, you've done something wrong. And then when you divide by the smallest number, we should be getting a relatively whole number. So obviously if I divide 0.0559 by itself, I get 1. And then if I divide 0.0559 by itself, I get pretty much whole number 7. So the X is 7. That's how I would do it. There are 7 H2As for every Na2SO4. Part D of this question is a reacting mass question rather than an empirical formula. So we've got a balanced equation and we're asked to calculate the mass of iron required to fully react with 4.9 grams of sulfuric acid. So the two things that I'm interested in are the iron and the sulfuric acid. I can ignore everything else. And I know that I have 4.9 grams of sulfuric acid, and I don't know the mass of the iron. So it could be that you've been taught at GCSE to do 2 lots of FE and work out like the formula masses on both sides. We want to do this using a mole calculation if we can, because everything that you do further down the line is going to involve mole calculations. So therefore, if you stick to using the same technique, even if it's very slightly different or harder than what you're used to, it'll make things a lot easier in the long run. So the first thing I know is I know the mass of sulfuric acid. So if I work out the formula mass of sulfuric acid, I can work out the moles. And at this point, I'm not using the balancing in the equation, just the formula. So I'm just working out the formula of H2SO4 and ignoring the 3, we'll come back to the 3. So turns out if I add it up, the MR of sulfuric acid is 98. So my moles of sulfuric acid is therefore going to be the mass I've got, 4.9 grams, divided by 98, which gives me 0.05 moles. Sensible number. These numbers are usually quite small. Now I'm going to use the equation. So the equation tells me that 2 moles of iron react with 3 moles of H2SO4. That's my ratio. And I'm told I have 0.05 moles of sulfuric acid, or I've just worked that out. So I can then work out this ratio. So this is a 2 to 3 ratio, which can often mess with people's heads. There's 2 things you can do. You can either divide both sides by 2, and then you have a 1 to 1.5 ratio, in which case, to get from there to there, I divide by 1.5. Alternatively, you divide by 3 and times by 2, which is exactly the same as dividing by 1.5. So whichever way you do it, you either times it by 2/3 or you divide it by 1.5, you still get the same answer for iron, which is 0.0333. So you can check after you've done that and think, does that make sense? I should have a smaller number of moles of iron, but it's more than half the number because it's 2 to 3. So yeah, that is 2/3 of 5 is going to be 3 1/3. So that makes sense. That's my moles of iron. Therefore, my mass of iron is just going to be how many moles? 0.0333 times by the mass on the periodic table. Again, this has given you A-level 55.8 is from the A-level periodic table, but you'll still get pretty much the same answer if you round it to 56. The next question asks you to calculate the volume of hydrogen gas by this reaction. So notice in the question that we have not gone on to a second part. So we were on part D, and we were part D II. Now we're on part D, we're on part I, and now we're on part II. So when you have like something happening like that, when it says part II, what it means is you need to use the information from the previous question, or some of the information, some of the numbers are going to be important. If it were to suddenly change and go from part A to part B, it means it might be talking about the same chemicals, but doesn't necessarily require the same numbers. That's a really useful exam tip. Works at GCSE too. So this time it's the volume of hydrogen gas that I'm interested in. And actually in the previous question, I worked out the moles of sulfuric acid, and I also worked out the moles of iron. So I know already that 4.9 grams of sulfuric acid is 0.05 moles. And I'm actually going to use that value because it's easier, because there are 3 moles of sulfuric acid to 3 moles of hydrogen. So they are the same number of moles. They're a 1-to-1 ratio with each other. So if I have 0.05 moles of sulfuric acid, which I already worked out, I don't need to work it out again, then I have 0.05 moles of hydrogen produced. Once I've got that, I'm simply going to do the number of moles times by the volume of 1 mole, which is 24, and that would give me 1.2 decimetre cubed. Don't forget, for gas volumes, super important to put the unit. You're not probably going to be given a little gap with the unit in it anymore, which you may have done at GCSE. You're now going to be left to your own devices a lot more with regards to unit, so you really get into the practice of writing them down. Notice I'm also writing them all the way through the calculations, just to remind you in your head what you're calculating each time, because a lot of the time people just do the calculations without writing whether it's moles, mass, volume, and then they get really confused as the question gets longer. So the next one, it says it's another one to do with a hydrated salt, and it's another one where we don't know what XH2O is. Well, actually it's really similar to one that we had before, because we've been given the number of moles and we've been given the mass in grams. So we can calculate molar mass, which is just what we call relative formula mass, or MR. So I can do that really, really easy, because the relative molar mass, the relative molecular mass, however you want to call it, is the mass in grams divided by the number of moles. And so it's going to be 12.25 divided by 0.025, and that's going to give me 490. And 490 is made up of Fe2SO4 3.XH2O. So you might be thinking, oh, I don't know what the dot means. It just means that those two masses are added together. So the mass of Fe2SO4 3 is added to however many waters there are, and the total equals 490. So I'm now going to work out what that bit weighs, because there's only one of those, there's not an X in front of that. So I'm going to add up 2 lots of iron, 3 lots of sulfur, and 12 lots of oxygen. So I need to know how to use my brackets to do that. That'll give me an MR of 400. What that tells me is that the mass of the water is 90 in every mole of this salt, and if I work out 2 hydrogens plus 1 oxygen, H2O on its own, just one of them, weighs 18 grams per mole. So I'm just going to see how many times 18 goes into 90, and it is 5. Therefore, my formula is Fe2SO43.5H2O.